I'm fine. Thank you very much. How are you?
Pretty good. Pretty good.
Oh, okay. So can you see the board now, right?
Yes.
Makes sense?
Title,
Cool,
introduction.
cool. So,
So how did you find the position in Chile?
after my PhD, I apply for a postdoc here. Every year here, there is a postdoc for the international candidates. And the good luck was that I got the postdoc for 2 years. And after coming here, I worked for 2 years. And then when I was leaving, I applied for the position.
Okay.
And again, second time, the luck clicked. And I was in Brazil. And so I had to come back here.
Okay. Where in Brazil were you?
I was in LNCC, Petropolis.
Okay. Very nice. Very nice. Well,
Yeah,
that's
in
something.
fact, I continued that work and that's going fantastic.
Very good. Very good. Fine, fine. Well, maybe that's something our young people should consider the possibility to look,
Yes, of course.
you know, look with the
It's
opportunity.
difficult for the theory to math pure it means, how do you say, not pure mathematician, for the people who does analytical mathematics, it's difficult to find a position. It's very difficult. So one must explore all the possible options, huh?
Yes, definitely. Well, this is certainly an option in a strange part of the world. How are you treated?
Oh, perfectly all right. There is no problem at all here. Only thing that people don't speak English.
Okay.
Yes, and if you are vegetarian, your life is difficult. The second clause.
Okay. Well, those are some things to note, but Spanish is not that far from English, is it? I mean, there are some
If
cognates.
somebody speaks a Spanish, it's easy to pick up the English. But if somebody speaks English, the going in that direction is difficult, bit difficult.
Yeah, but you went from Chile to Brazil, right? Brazil, they don't
Yes,
even
then I
speak.
learned Portuguese and then I speak Portuguese, Spanish, all. In fact, I can understand Italian as well.
Oh my gosh. Very nice.
No,
Very
but it's not a difficult job for Indians. For example, I born in Bihar and I took the birth and lines. I learned 3 languages immediately. From my father, one language, from my mother, another language, and they used to talk in a third language. So I learned 3 languages immediately.
Very nice. Very good.
So it's a bit easy for Indians, in fact.
Well, then you're lucky. Then people should consider these options in other parts of the world if that would suit them. Well, I think we can begin. I really should introduce you. Okay.
First of all, please introduce yourself. I don't know.
Oh, me. Oh, yeah. I'm Professor Jesse Deutsch.
Hi.
And hi,
Okay.
hello. Yeah, I'm a professor at SRM University, AP, Andhra Pradesh. I've been here about 2 years, and I've been for the most part having an extremely good time.
And how was the
Uh,
food?
yeah, well, fortunately, there's big basket, and a relative gave me a good hint of how to get the spice off
Yeah.
the chicken. Okay,
Yeah.
I buy chicken, it comes a lot of spice, and I put it in the refrigerator, and then if you put it in boiling water and let it go for 10, 15 minutes, most of the spice will come off, and even I can eat it.
So
Though
all my non-Indian friends, I have one suggestion. Whatever looks red in India, it's not tomato.
aha. Okay, whatever looks red, don't touch,
It's
huh?
not tomato.
It's not tomato.
It's not tomato.
It's red chili. Okay.
Yeah, because generally in the non-Indian foods, the red thing comes from tomato and it's attractive. So the audience jumps into the food immediately. So this is my typical suggestion. Whatever looks red, food it means. Red is not tomato.
I'll take that as quite the recommendation.
Oh, Tapan is here. And who else?
Sweta.
Sweta.
Yes.
How are you, Sweta? ¿Aprendiste algo de español o nada?
Poco.
Un poco.
No mucho. Poco.
Hi, Tapan. How are you?
I'm good, Ravi. How are you?
Fine. Thank you.
Yeah, welcome to this webinar.
Yeah, it's my pleasure.
Well,
So
muchas
it was planned on
gracias.
12th of February, but it's a summer vacation here, so I was available on 17th as well. Unfortunately, 19th I was not available, but it's okay.
Okay, let's
Yeah.
begin. Muchas gracias, Professor. Much thanks, Professor Ravi Prakash, for showing up to give us a talk. Let me quickly go over a short introduction. Since 2016, he's worked as an assistant professor in the Department of Mathematics, Faculty of Physical Science and Mathematics, University of Concepcion in Concepcion, Chile. He finished his PhD in 2013 from the Department of Mathematics, Indian Institute of Science, Bangalore, India, under the guidance of Professor A.K. Nandakumaran. His research interest lies in the area of homogenization of optimal control and optimal design problems arising in the context of PDEs with a domain having oscillating boundary. So which sounds all fascinating, so without much further ado, I'm going to let Ravi Prakash have the floor. Professor Ravi Prakash will have the floor, and he's going to tell us about Introduction to Homogenization Problem and Tartar's method. So please take it away.
Okay, thank you, Professor Chase. Thank you very much for the introduction. It was quite long, but I don't know, it was necessary. Yeah, so I'm not, it's clear that I'm not going to talk about my research. My research lies in homogenization, optimization, inverse problems, blah, blah, blah. So I'm not going into my research. I am just trying to introduce you the homogenization problems. Okay, what is homogenization? And in this talk, we will see a very easy example of one dimension. Okay, and we'll see one method was introduced by Tartars, and just to have a feeling that what is homogenization method is. Okay, if somebody wants to explore my research, please be my guest and go through the Google search. It's not difficult to find out. Okay, so homogenization is the area where I started my research career in around 2009 or something. First paper came in 2011 or something. Okay, so to understand homogenization, definitely there are lots of people working in India, like my PhD advisor Nanda Kumaran, and Vidhan works there from IIT Roper, no? And Nanda Kumaran is there from Muthu Kumar is there from IIT Kanpur. So at least I will try to make all of you eligible, make all of you capable enough to understand whatever talk you listen in the future on homogenization. Okay, we will not go in these all theory which I am going to show you today. You can find it in the book of Benson, Lyons, and Papanikolaou. I took it from this talk, or I learned personally this topic from Giransky and Donato. And there is one my advisor's overview of horizon. You can find it on the website of ISC as well. So these all things are available in the internet. So if you want to go through personally on the topic, please you can pick any one of these 3 books. Okay, so first of all, let's so homogenization. This mathematical part of the homogenization started in the 70s, and one of the pioneer researchers were there. Tartar was there, and from Carle Mellon, and another guy who was actually the batchmate, Francois Murat. He was from France. And both were actually students of the famous guy Lyons, field medalist, everybody knows. So this is mathematical theory started from there, and basically they were trying to analyze the optimization problem and landed up because Lyons was famous for the optimization problem. You can see his books on many topics, for example, optimal control as well. So so these guys were trying to do optimization problem, and they were landed in something called homogenization theory. Homogenization theory is not new for the engineers. They used to do lots of things. For example, there is a very funny thing happened when I was starting my career. I was searching homogenization. I found there is a method of extracting cream from the milk is called homogenization. And I got stuck at that time that what is this? Then I started understanding that mathematical theory of homogenization is something, the same philosophy, but we will use here the advanced mathematics. That's it. So one very famous example used, very famous prototype used by the engineers to do the homogenization was constructing the composite media. Yeah, everything is audible, right? You can listen to me, and the picture is clear, right?
Yes, yes.
Yeah. Okay. So the composite media. In the composite media, it's the picture which you are seeing right now. You can think like there is a square, right? And in the square, there are 2 materials. One is inside the circle and one is outside the circle, right? And using these squares, I am trying to construct a bigger circle. Okay. So what I'm doing, suppose we have a square. I am scaling it with the very small parameter epsilon and placing it side by side, okay, and trying to construct a domain which is circular, bigger circle, and trying to and that bigger circle will be my composite media, composite material. Why I'm calling it composite material? Because in the circle I have a different material, outside the circle I have different material, and then I'm clubbing all the squares to form a third type of material, right? So if suppose you are talking about the conductivity, okay, so in the square you know the conductivity. Yeah? There are 2 conductivities. I'm presenting you a simpler example. You can think about difficult ones. It means you can take a square, divide it in many parts and many materials, and then construct a bigger circular domain which it will be like have multiple characters, right? So let's talk about the conductivity. If you have a known conductivity in the square, you can know the conductivity of this circular domain, right? Point wise, correct? Even this, if in the next part, if epsilon goes to 0, if you see the square is going smaller and smaller, right? So if you want to compute some PDE, for example, using FEM or whatever, right? You have to take the step size very, very small, correct? And when epsilon goes with very small, your computational cost goes higher, correct? So beyond one level, you cannot compute the actual behavior of the composite, correct? What do you mean by you cannot compute? It means that you cannot, for example, if you are talking about thermal conductivity, you cannot talk about the temperature, correct? Even if you are knowing point-wise behavior of the conductivity, correct? So you can represent it for a simple example. Suppose you have a sine function, correct? Epsilon is equal to 1, correct? If you scale it by epsilon, so it will be sine of x over epsilon, correct? Then you try to try to draw it. When epsilon is 1/5, if you can see, it's getting it is getting more oscillator, correct? If you go 1/10, it is more. If you do 1/10, it's more. 1/20, it's more. And then slowly you cannot compute, correct? The value, the computational people can understand easily that the value comes 0. When epsilon goes smaller and smaller, the average variable comes in, right? It becomes 0 eventually, correct? You agree? Then what is homogenization? Then if you if you have something, I'm talking in the sense of PDE. Okay, so let's go back again to the composite material. Composite material with this microstructure. Okay, microstructure, I'm denoting it by PDE subscript epsilon, correct? So we have a PDE subscript epsilon, and we saw that at least one difficulty we saw just now, that we cannot compute the global behavior of that material. Okay, so homogenization, what it does, okay, forget that PDE. I will give you some hypothetical PDE or some model which will be approximately tell you what was the behavior of PDE sub epsilon. You agree? So homogenization theory basically is about giving you a model, okay, which can replace where you can just skip the difficulty which appeared in the model because of the small parameter epsilon. Okay. Now mathematics come into the picture, that when you say approximate, all right, you have many difficulties, right? Mathematical issues. How in which sense you are saying that it's approximate, right? Then asymptotic analysis comes into the picture. Okay, and an asymptotic analysis will give you will start with the PDE, do the asymptotic analysis, and then you will get a limit PDE, and that limit PDE, you in the asymptotic analysis, you shows that under some norm or in some space, both PDEs are approximate. Okay, so this is just one example of the difficulty why homogenization comes into the picture. There are other difficulties. For example, you have a PDE, okay, and for example, metamaterial. Okay, you have metamaterial, you want to design a metamaterial, which is right now the project I am involved in. So that metamaterial, if you want to design, what will be your approximate design? So as in the first part I explained that you have PDE with the epsilon, and then you approximate, you give a PDE without epsilon, and you said both are same, both are approximate, correct? The another way is that you have a PDE, and then you say, okay, give me a PDE depending upon epsilon, which approximate the limit PDE. So this is called the inverse problem, right? So in many cases, some asymptotic analysis you do for the forward problem, and in some cases you go for the backward choice. You look for some approximate. Okay, this comes under the area of inverse problem, right? Sometimes when you do optimization, again you have a limiting behavior, correct? So in that limiting behavior, epsilon appears. So the homogenization alone is a subject, but it has a relation with lots of classical areas like inverse problem, optimization problem, blah blah blah. Okay, so the aim of this project is the mathematical. What I am trying to introduce, what is the mathematical theory of homogenization? Okay, and the first method which was introduced by Tartar. How can we analyze this asymptotically? Okay, yeah. So as I told you that we have a PDE depending upon epsilon, and then we define a PDE independent of epsilon, and we say that is approximate. So this PDE, which is the limit PDE, which is independent of epsilon, it is the effective behavior. It shows the effective behavior of heterogeneous media in general, not the average behavior. And theory of homogenization is useful to characterize these behaviors and has to reaching applications in many areas like composite media, porous media, analysis of thin structure, to name a few. Okay, so it can be understood that it can be understood easily that effective the PD which I am giving you, which is I'm saying that it will behave approximately as a PD depending upon epsilon, is the somehow trying to capture the average behavior, okay, of the material which has a microstructure. Okay, so there are lots of other things which we can do with the homogenization. Okay, so I am not telling here that homogenization is all about the composite material. No, not at all. Or I am telling the homogenization started from the motivation of the composite material, mathematical theory in the 70s. Okay, then porous media came. Porous media, it means you have a big domain with lots of small holes. Okay, one thing also to be observed here, if you remember the first picture where I showed you the composite media, I placed the squares in the periodic manner, right? Right, but you can think about a composite media independent of periodicity. Make sense? For example, the very famous thing which we do from the birth, making a ornament. It's always 22 karat, right? It's a composite media, right? It's never 24 karat gold ornament, right? It's the composite media, but this is not periodic, obviously not, right? So so periodicity is the necessity of the mathematical analysis. Okay, but there are few papers which says that it's quite relevant. If you can do analysis with the periodic structure, you can generalize it for the for not all results, but a few results for the non-periodic case. Okay, but there is also a question of non-periodicity. How will you define non-periodicity using mathematics, right? In the periodicity, mathematics well defined. F is periodic if f of x plus t is equal to f of x, right? Periodicity is very well defined. But non-periodicity, you have to define using mathematical tools, right? So, for example, if you have if you want to talk about the conductivity, correct? So, for example, sigma represents conductivity, right? If it is periodic, you will get sigma of x over epsilon, right? Because you scale the square with epsilon, and then you placed it periodically, right? So x over epsilon will capture the periodicity. Okay, we call it microscale, correct? But for example, if you have non-periodicity, for locally periodicity, for example, we call it locally periodicity, then you call sigma of x over epsilon. One thing you can immediately notice that x represents the macro coordinate, right? X over epsilon represents the micro coordinate, correct? So if sigma depends upon x and x over epsilon, it means conductivity of this guy, this composite material, depends upon two things: x, the coordinate there, and x over epsilon. X over epsilon is the coordinate in the reference square bracket, right? Which we scaled and placed periodically, correct? So these, so similarly, from locally periodicity, we are just drifting a little bit away from the periodicity, right? For example, what is the sigma x over epsilon? You can see like sigma 1x multiplied by sigma 2 of x over epsilon. Sigma 2 is epsilon is periodic, and sigma 1 is capturing the behavior of the macroscopic scale, correct? So there are some drift, right? So mathematically, if you want to talk about non-periodicity, definitely you have to define in which sense you are trying to mathematically formulate the non-periodicity. Correct? Makes sense? Okay. So there are a few points which I wanted to mention. You can read more about replacing the problem by limit one can easy numerical computation, which I was trying to tell you in the beginning, right? There were mathematical computational difficulty, and then you can replace that by using the limit problem. Okay, for Sweta, FEM is not going to work right now in a simple form, right?
Okay.
So still I don't want to drag you there, but I'm trying to give you a feeling that multi-scale FEM has issues. Okay, and there are some things which is I'm trying to see, but I can tell you right now that if you are thinking the multi-scale FEM is the solution of this guy, you have still the issues.
Multi-scale or adaptive FEM you're talking about?
Multi-scale.
Okay. Okay.
Yeah, because multi-scale, why? Because you have to capture the two scale, no, the x thing and x over epsilon thing at the same time.
Yes.
Okay, but still there are issues in defining the basis functions. Okay, so those things are really open, and people are rushing for that. Okay, people are rushing for that because, and especially when you go little bit away from the composite material and go for the oscillating boundary problem, which is really my area of work, then the difficulty is of different level, because you see here, when you change the epsilon towards 0, your microstructure changes, correct? But you have, when you have oscillating boundary domain, your whole domain changes.
Yes.
So the difficulty is of another level in homogenization if you go from the composite media to the oscillating boundary domain. Okay, so we can talk about it later. Yeah, motivations. So motivations I already gave you a lot. Homogenizing basically the mathematical process. So to understand homogenizing material with highly oscillating heterogeneities via the homogenization material, mathematically it is a limiting analysis, which I told you earlier. Yeah, for the physical problem, you can as I told you, that optimization problem, inverse problem, differential integral equations, these all things are very involved. Okay, so in one line we can say homogenization deals with the study of of such solutions and obtain the equation satisfied by the limit. Here the limit PDE is the if you will reach to the limit PDE using the asymptotic analysis, correct? But you know, when asymptotic analysis gets involved, you have to select the space very carefully, correct? Sometimes L2 space, H1 space will not work. You have to go to L2. If sometime L2 not work, you have to H-1. As soon as you go towards H-1, the computational guy will get terrified. Okay, so we have to take care of both. As soon as we are trying looking at this issue from the computational aspect, we have to be very careful on these issues. Okay, let's go for the technical details. Quickly, we recall few things from the guys who in this presentation who are not from the mathematical background or are out of touch. Let's recall quickly what is H1 space. H1 space is the energy space with the derivative also in the energy space. H10 is the same H1 space, but the boundary value of the function is 0. H-1 is the dual space of H10. And here I was telling you the square, right? A small square. That is square, or you can say rectangle, we in n dimension, we can represent by y, the reference cell. Okay. And any periodic function, y periodic function will be like kx plus kliei is equal to fx almost everywhere in Rn for k belongs to any integer. Okay, so C infinity periodic, C infinity for y is the C infinity functions which are periodic. Quotient space is the H1 periodic y, quotiented with respect to R. Okay, now let's go and define the problem. Okay, let's go and define the problem and then try to analyze this for the very simple case of 1D. And then in the last of the part of the talk, we will see little bit of technical things. Okay, I took care of the audience because you have a very diverse audience. I took care that we should not go into too many details, but don't worry, just try to understand the philosophy. If you I'm just trying to make you understand that even the next time when you see a lecture on homogenization, it will click to you that okay, I got the idea. So let's try to frame it. If you did not understand the technical difficulty, it's fine. I will try to explain in the simple words at each step so that if you did not understand the mathematical issues, no problem. It's just that you have to go through it once you need. Okay, so let's define the problem. Here there is a space of the matrices. Okay, and these matrices are elliptic and bounded, and this matrices will with the diffusion matrix. It will define the characteristic of the material if you want to visualize it. Okay, so this A epsilon I am defining as the diffusion matrix with the microstructure, which is capturing the properties of the microstructure. Correct? A epsilon ij x. If it is periodic, definitely A epsilon ij will be A ij of x over epsilon. Make sense? Okay. And if we talk about the elliptic problem, then it will be minus divergence of A epsilon of gradient. It will be an operator. Correct? If you talk about the thermal conductivity or elasticity, blah, blah, blah. So it will, the equation will be your minus divergence of A epsilon of gradient of U epsilon is equal to F in omega. In omega, if you want to really understand, that was the big circle, right, which we constructed. And U epsilon is equal to 0 on boundary. So it's a homogeneous Dirichlet condition, and you have minus divergence of gradient A epsilon of gradient U epsilon is equal to F. Okay, and it has a solution. It is very well known from Lax-Milgram. Look, it's very famous Lax-Milgram lemma, but I really feel that it's a so important lemma that I call it theorem. And in some books also they call it theorem. So Lax-Milgram theorem gives you a solution for this problem. Okay. And bound comes automatically from the Lax-Milgram lemma. Okay, U epsilon S10 omega is bounded by C. Here, point to be noted that C is independent of epsilon. Why it is clear? It is easy to observe C is independent of epsilon, because you see A epsilon is the bounds alpha and beta is independent of A epsilon, right? The diffusion matrix. So using Lax-Milgram lemma, you can easily found the bound for U epsilon is independent of epsilon. Correct? Then we can find that up to a subsequence U epsilon prime is converging to U0 weakly in H10 omega. Okay, if you are not familiar what is weak convergence, just think that average of U epsilon prime is converging to average of U0. Forget whatever difficult technical things I'm saying, it doesn't matter. Average of U epsilon prime is converging to U. It's not 100% like this, but I'm just saying you to avoid the technicality of weak convergence and blah blah blah. So U epsilon prime is converging to U0 weakly in H10 omega. Now let's define the operator. What was this minus divergence of A epsilon of gradient U epsilon, correct? So A epsilon of gradient U epsilon, we are represented as Xi epsilon, and this Xi epsilon is A epsilon. We are trying to write the equation in this with the help of Xi epsilon, right? So Xi epsilon gradient of V is F of V. Again, Xi epsilon is bounded, correct? Xi epsilon is bounded because it is equal to F, right? So we can take the modulus both sides and apply the Cauchy-Schwarz. That's it, finished. So Xi epsilon prime will converge to Xi 0. Now, if you notice, using this weak convergence, we can find that Xi 0 satisfies the PDE minus divergence of Xi 0 is equal to F in omega, correct? So this is your limit PDE. What is the difficulty? How is it? What is the solution of Xi 0? Correct? And how this Xi 0 is related to U epsilon? Correct? This is the main issue, because you started with the PDE whose solution was U epsilon. Correct? And you are trying to find the limit PDE of that epsilon dependent PDE. Correct? You got a PDE. Correct? Fine, without any difficulty. But you have to find the relation between Xi 0 and U0, right? Because U epsilon was converging to U0, correct? So you have to find the relation between Xi 0 and U0, and if you can find it, you have got your limit PDE. Make sense? Okay, So in general, A epsilon, if A epsilon is converging to A hat strongly, for example, the diffusion matrix, your diffusion matrix A epsilon is converging to A hat very strongly. If it is not very strongly, sorry, strongly, what is very strongly? It's strongly converging. Then it's very easy to pass the limit and very easy to find xi0. What is xi0? Correct, because if you will write weak form, and immediately weak form will tell you that xi0 is A hat gradient of u0, because A epsilon is converging strongly, U epsilon is converging weakly in H1. So you can weakly strongly we can pass the limit, and then we can get the limit PD easily. But unfortunately, A hat is this convergence of diffusion matrix is never strong. Okay, and here it makes the area of homogenization strong. It means sustainable. It means makes sense in this earth. If we can, it is a very famous issue. Weak cannot. If you weak we cannot. If we have two sequence of with the weak convergence, we cannot pass the limit. Correct. So here it was strong and weak, so we passed the limit and got the solution. But a strong convergence of diffusion matrix, I'm saying it's not practical. So we have two sequence with weak convergences, so we cannot we cannot pass the limit. So we have to do something to, and if we cannot pass the limit, we cannot find the xi relation between xi naught and u0. Correct. So for that we have to do something. Correct. So let's go first of all in the periodic setup and try to reframe the problem, and then see 1D example, which is very easy, and then see the Tartar methods for the Rn. Okay, so in the periodic case, as I explained to you before, your diffusion matrix will have the form A epsilon x is equal to A of x over epsilon. Correct, because in the periodic case we take a square, we scale it by epsilon and then place it side by side. Correct. So if in the reference cell, if you have a coordinate y, correct, so if you scale it epsilon y and then place it side by side, so x is equal to epsilon y. Correct. And x by epsilon is y. Correct. So so you have a diffusion matrix. A epsilon f in the periodic case will look like A epsilon j A ij x over epsilon. Make sense? If you have understood this, how the periodic structure looks like, then your half of the picture of the homogenization is clear. Okay. So now you have a particular structure of the periodic case. So let's get back to the statement of mine where I was telling you that for the non-periodicity you have to define the non-periodicity mathematically. Correct. For periodicity it was very easy. We just define it using scaling x over epsilon. Correct. But for the non-periodicity you have to define it in some way. Correct. So we defined it, and then it is very well known that if you have a function f periodic in y, so f of x over epsilon will converge in weakly star to L-infinity omega to its average. Okay, so f of x over epsilon will converge to the average of f weakly star in L-infinity. Okay, it's a very famous result. So this result is the key for the analysis of the one of the keys to the analysis of periodic phenomena. Okay, so we will use this. So your A epsilon is defined as A of x over epsilon. Correct. So it will converge to mean of A, correct, over y. Okay, in weakly star L-infinity. Okay, so now let's go and see one-dimensional problem. It is so divergence is minus derivative of means minus derivative of this, right? A epsilon is your scalar now because in one dimension you are in one dimension, so your diffusion matrix became one-dimensional. Okay, so this A epsilon is your A epsilon has the form A of x over epsilon because we are talking about the periodic case. Okay, And then gradient became the one derivative. So your problem became very simple. Minus derivative of a epsilon of derivative of u epsilon is equal to f, and u epsilon on the inside 0. On the inside 0. Now, can you solve it for me in 2 minutes? It's very easy. You just need to use the fundamental theorem of calculus and one of so I can do it for you here. So I can write this problem as d of u epsilon dx is equal to integral over f 1 by a epsilon. Okay, I'm not writing the integral constant because integral constant will go to 0 because you have a homogeneous condition, right? So, so it is like this, and then again using the fundamental theorem of calculus, you can write integral of 1 over a epsilon integral f. Correct? Very easy. And now 1 by a epsilon, if you know that a epsilon, we can write b epsilon x is equal to 1 over a epsilon x, correct? And this is equal to 1 by a of x over epsilon, correct? So b epsilon is also a periodic function, correct? And b epsilon x has some b of x over epsilon, correct? So we can again convert b epsilon converts to its average, correct? So 1 by a epsilon will converge to one average of 1 by a. Fine. Weekly. Correct. So we can write that u epsilon converges to u0, and this will converge to integral of 1 over a. Just a moment. I need to make it a little bigger. So this will converge to 1 over. It will converge to mean of 1 over a, average of 1 over a, and integral f. Correct? So again, let's formulate it back. You will get d of dx of 1 by mean of 1 over a, du of dx is equal to f. Correct? In 2 minutes. So you started with this epsilon level problem and you reached up to this problem in 1D. Easy. Okay. And one thing to observe, you know, a epsilon was a of x double epsilon, correct? A epsilon converges weakly star L infinity to mean of a, correct? And u epsilon converges weakly in H1 to u0, correct? So a epsilon was converging to mean of a, and du epsilon dx was converging weakly to du0 dx, correct? But the problem was that we could not pass the limit because they both were weak, correct? So we adopted some other method, right? But one thing to observe, 1 by mean of 1 by a is not equal to mean of a. That's the mistake engineers used to do when they used to do the homogenization before the mathematics come into the picture. They used to take it the mean of a, but here we are observing that it's not mean of a, it's the naturally it should be mean of a, right? Because a epsilon converges to a mean of a, derivative of u epsilon converges to derivative of u, so it should be mean of a product derivative of u, right? But it's not. Why? Because weak, if we have two weak convergences, we cannot product cannot go to the product of the limits. So here we observe that it's not mean of a, it's 1 by mean of 1 by a, right? It indicates that we need to do some work, mathematical analysis, because what looks natural is not always the truth, right? So this problem we observe very clearly that what is in the language of Thangavelu, he used to say whatever trivial looks is never trivial. So it was looking trivial to engineers that the coefficient matrix converges to mean of a, but this is not true. It's 1 by mean of 1 by a, which is never equal to mean of a. Okay. So why the differences appear? Because we have the classical difficulty. We have two weak convergence sequence. The product of two weak convergence does not go to the product of the limit. Okay. So let's go and see further. And in the form of theorem, we can write that if f is in L2 d1 d2, a epsilon defined as ever, like periodic, a epsilon is equal to a of x over epsilon, u epsilon is the solution of the 1D problem, then u epsilon converges weakly to h1 0 d1 d2, and the limit problem is like equation number 21. Okay, which I was writing in a very beautiful handwriting. Yeah. Yeah. So just by this model, let's go back, which we discussed before, and try to understand what happened. Here, what happened is that we started with the 1D ODE, second order, and then we landed up in a ODE, which we are saying that will replace, or which will behave approximately in the same way as the epsilon dependent 1D PD. Okay, and we observed here also that it's not so trivial. We have to do the mathematical analysis to reach up to this point. Okay, makes sense? Now, let's see the proof of the same 1D problem in the framework of ND problem. Okay, n-dimensional problem. Why I want to show you this proof? Because later for the n-dimensional problem, Tartars will use the similar technique. So once we will be familiar with 1D, definitely ND will be some sort of familiar, some sort of understand we can connect with. Okay, so u epsilon converges to u0 weakly. It is like always true, obviously true. From the lax milligram, you can get the bound and convergence will appear. Again, in the same way, we will define xi epsilon, a epsilon derivative of u epsilon, and then we can write the equation, 1D equation, in the form of minus the derivative of xi epsilon is equal to f. Correct. And then xi epsilon's bound will get the bound of xi epsilon, and xi epsilon converges weakly in L1. Now, since xi epsilon is H1 bound, we will get the strong L2 bound. Correct. If we have a weak convergence in H1, you have a strong convergence in L2. Correct. If you are not understanding the details, please don't worry. Okay, these things we have to make the hands dirty when we go into the details. Okay, so this is a compact embedding of L2 space in H1 space, or weak convergence becomes strong convergence. Okay, so these things are very well known for the functional analysts who are from not the functional analysis background. Please don't worry. A strong means you understand almost everywhere pointwise. Okay, what is almost everywhere, forget it. If you don't understand, it's okay. You think that xi epsilon converges to xi 0 pointwise. Happy, be happy. Okay, so I can again write here derivative of u epsilon is equal to xi epsilon 1 by a epsilon. Correct, which I was showing you, right? So again, xi epsilon will 1 by a gradient 1 by gradient of a epsilon 1 by a epsilon will have the bound, because a epsilon was having the bound, so away from the 0. So 1 by epsilon will also have the bound. Okay, and then a epsilon will converge to the average of 1 by a. Okay, a 1 by average of 1 by a will not be 0. Why average of 1 by a will not be 0? Because we saw the bound is away from 0. Right? If some function is bounded away from the 0, the average will never be 0. Correct? Make sense? If some function is positive and strictly away from 0, its average will never be 0. Correct? So this is very important, because we will see why this non-zero is very important, because it will help us to go back to the limit OD. Okay, so it's clear that derivative of u epsilon will converge to mean of 1 by 0 and xi 0. Now we have to find the relation between xi 0 and u0, and if you find that, we are done. Correct? So just by from 22, equation number 22, derivative of u0 is actually the mean of 1 by a product multiplied with xi 0. So, okay, and since mean is not equal to 0, we can take the mean on the other side, correct? And if you take the other side, you will get actually the limit PD. Here, I am trying to remark the very important issue, which I was indicating verbally before, that mean of 1 by mean of 1 by A is not equal to mean of A, correct? And second issue was the product of two weak limit is not the product of two limits. Okay. Now, so this is clear. And suppose if A epsilon is not periodic, okay, A epsilon is just your any diffusion matrix depending upon microstructure, but it is bounded away from the bounded away from 0. But here you see, we don't need to worry too much about how do we define the non-periodic microstructure. Why? Because it's one dimension. In one dimension, what maximum, there are not too many things to play, right? But here I'm presenting you so that you can have a understanding that you just need one look by bound. We can say that B0 exists, correct? B0 exists. Okay, so in the limit, you will find the limit problem in terms of B0, correct? But how to compute B0? There in the periodic case, you were having B0 is equal to mean of 1 by A, correct? Here, we don't know what is B0. We can only say, okay, B0 exists, correct? But we cannot say that what is B0. So in some sense, the limit PD, which is written below, is not complete, correct? It's not clear what is B0, okay? And you will find Vaninathan talking many times on this topic, the optimal design, right, in RN. So what is the optimal? He also a separate research area, and this is called optimal design, where you try to find out what is the best possible bound of this limit diffusion matrix. Okay, the difference in the main issues which I told, I don't have much time, so let me go very quickly to the Tartar function. Okay, how much more time I have?
I think about 5 minutes, and then 5 minutes for questions.
Okay, so I will take just 5 minutes. Okay, I will just try to indicate the what we are. So up to 1D, it is very clear, right? If you see, even in 1D, if you have non-periodic structure, you cannot find precisely the limit P problem. Correct. Let's go to the RN thing, and you see the Tartar method. Tartar used his method to resolve the issues. Okay, he used the method of auxiliary functions. We also call it cell problem, solution of cell problems. He tried to capture the difficulty at the cell level. Okay, in the general language, if I say, of course there are details, we have to go into that. But the idea was to the main issue, as I indicated before, was the weak convergence. We cannot pass the limit if we have two weak convergence. So he tried to define some cell problems and tried to observe the difficulty from the epsilon level and try to pass the limit using these auxiliary test functions. Okay, so for that he defined some periodic cell functions in if you see here, he is trying to define in the cell Y. It is not in omega, it's a reference cell. He is trying to define auxiliary test functions, correct? And using this test auxiliary problems, he is trying to define just a moment here. He is trying to define the test function. Okay, and this test function will observe the difficulty which was appearing before. Okay, it will observe the so in general when we discuss homogenization, we always try to define a test function which can capture this such type of difficulty. Okay, I'm not talking about this method worked somehow for the porous media, But as I was indicating to you that from porous media, if you go to oscillating boundary where I work, even when epsilon changes, whole domain changes. Whole domain changes, it means your whole space, whatever space you choose, it will change. Correct? H1, if you choose H1 omega epsilon, if you change epsilon, H1 omega epsilon will change, right? So somehow you have to go to the extension operator or some different type of ideas. Correct? So the history changes when you go from normal homogenization problem like composite or porous media to the oscillating boundary domain. And that I was indicating to Sweta that when it goes, the discussion goes for the FEM for in the direction of homogenization. Oh, life is little bit complicated. Okay. So let me just quickly go there and try to define the problem. See, if you see here, he got the limit problem, correct? But this limit problem, here the diffusion matrix has contribution from the reference from the solution of the cell problem, correct? So this is in other words, without telling you the detail, I was telling that this reference, the cell problems, we are trying to capture the difficulty which was appearing at the epsilon level. Okay. So, and why it is captured, the cell problem is this appears in the diffusion matrix because the problem was the epsilon was contributing into the diffusion matrix. If you remember, a diffusion matrix was defined A of X over epsilon, correct? So it was actually the source of difficulty. So the test function tried to absorb the difficulty which was created by the or integrated into the system by the diffusion matrix. Okay, and that's why in the limit problem, the diffusion matrix has contributions from the reference cell solution. Make sense? Okay, so my time is up here. So if you have any questions, please let me know. Thanks for your attention.
Thank you.
Thank you.
Thank you.
Yes.
Any questions?
Questions?
So in moving domain, for your oscillating boundary, like, are you using some reference cell to map it again to?
Earlier, when I was started my PhD, I used.
Okay.
But
So
then I defined recently, which I published was completely nonlinear. Completely nonlinear.
non-linear problem on a moving domain, right?
Moving domain is the next. It means moving domain. Look, if you are saying that your domain is moving.
No, your boundary is moving in your problem, I think.
No, it's like you have a reference cell and then you scale it and form the boundary.
Okay.
Your boundary is fixed, but it has wrinkles, just like comb. In comb, you have microstructure, right? Oscillating boundary, but it is fixed, correct? What you are trying to say is next level. You have to go to the sea surface, and if you want the sea surface, and then try to analyze something.
Yeah, actually, my work was on moving domain, so I was surprised. Yeah, I was.
No, but that is a problem which we call moving boundary problem.
Yes,
that is an optimization problem. And there, if you have microstructure, bang, here you are. If you can do this, you are in the cutting edge defining. This is just now I'm trying to do with the Maxwell's equation. But unfortunately, it took me 4 or 5 years just to define the problem. I don't know how much more years I will take to solve. But if you can do it, you are at the cutting edge. You will be the leaders.
Yeah, no, I worked on very basic. Just use some stabilization. I don't know about this, so I was just asking, like, how did you manage with the moving domain? That's what I wanted.
Stabilization is the soul of the optimization problem. It all starts from there.
Okay.
It all starts from there. It means you can, for example, linearization is some sort of stabilizer. Some sort of. I'm not telling you in exact words.
Linearization. I don't know in the context of
if you want to deal with the non-linear problem, okay?
Yeah.
You have very less theory, very less.
Yes. Usually we work on, even I worked on viscoelastic fluids. So there what we do is we substitute non-linear term to a linear term just to easy.
Here starts the drama.
Things easy, yeah.
Here starts the drama. So we as a mathematician don't have too many things to do, even as a computational. When it comes to the non-linearity, सब हाथ उठा देते हैं, बोलते जय श्री राम, हो गया.
Jai Shri Ram. That's true.
Then it's like, but still somewhere like Maxwell's equations and something like that.
So Maxwell equation is only like, is it not a set of equation? Like
it's a system, yes.
System of equation.
Yeah.
Only one equation, or like you have
it's a system of equation.
Okay, I'll see that. I don't have idea about.
No problem. So just now, it took me, defining problem took me 6 years, and I don't know. I am just defining it. Just defined it. Okay, it took me something, but it is not alone the homogenization. It's about the homogenization with optimization. And now what? So if you got the feeling, right? So he was trying to solve the issues of the macroscopic level using the cell problem, correct?
Yes.
Now what I'm trying to do is that in the same problem, if you optimize something, can you get up to the some level, or can you reach up to the something? It means you are trying to control at the microscopic level and try to get some desired macroscopic behavior. You understand?
Yeah.
So it's just now it's for example, you must have seen there is elastic body, right? If you elongate the elastic, can I just remove the slides and talk to you?
Yes.
Like this? Where is that? I don't know.
In fact, it appears to be 6:30. We can close this.
Yeah, sure. We can talk some.
But those who wish to continue to talk, I'll let the seminar run